Now this method though, then, are generally considered to be reliable up to about 50,000 years. So that's, roughly 9-ish half-lives or so. And once you get out past 9 half-lives, now you've taken that amount, you've cut it in half 9 times. So it's gotten really, really small at that point, right? So it just makes it hard then for you to distinguish, the little fine details, how much is actually left. Now the other kind of, I don't know if it's controversy per se, but the other kind of concern though with radiocarbon dating is we have to make some pretty big assumptions. One is we have to assume then that over the 50,000 years or 10,000 years or whatever it was, there was no other source of carbon-14 then that was introduced into the sample, or there was no other process by which carbon-14 then was lost. And we also, of course, we are assuming then that plant or animal did have the standard 15.3 to begin with, and things like that. So, but again, it's roughly good enough when you're kind of. I mean, it won't tell you down to the exact day or the month, but it'll tell you, roughly how old it was within 10, 20, 50 years, maybe 100 years, which is fine when you're dealing with things that are 10,000 years old. 100 years is. And here's, by the way, Stonehenge. How do they date Stonehenge? Stonehenge is made out of rock. There's nothing plants or animals in there. Well, the way they did Stonehenge was they found various tools around it that are made out of bone and wood and things like that were used to build Stonehenge, so they could date those once living things, and they could do that then to help date places like Stonehenge. So, okay. Well, let's try to use this. I'm not reconnecting here at all. I may have to give up. So let's say you find a piece of wood out of a tomb, and it's only got 1/8 of the activity of normal living animals and plants. So the piece of wood would normally be at 15.3. Now it's at 1/8 of that. Well, how many years ago? So remember I mentioned before that if you look at your periodic table, which you'll want to pull out here shortly, all of the elements after uranium, none of those exist naturally. So our table goes up to 118, but only up through 90, was that 92? What's uranium? 92? Yeah, 92. So all the ones from 93 to 118, all made by transmutation. So what is that? 26 elements. So 26 of them don't even naturally occur. They had to be made by transmutation. So, for example, Rutherfordium, named for our buddy Ernest Rutherford, it was made artificially. How was it made? Well, they took californium-249, and a little piece of carbon, and they slammed them together at warp speed, and they collided and spit out a Rutherfordium and 4 neutrons. This is the kind of thing that goes on then in these big giant machines called particle accelerators or cyclotrons. They have one up at like a Stanford and Lawrence Livermore and CERN over in Switzerland, and there's one that's like 5 miles wide, 5 miles wide in diameter, and back in Chicago, underneath like Northwestern University. Basically what it is, it's just this giant tube, either a long one or in a ring, and they'll take one of these, and they will just basically whip it around as fast as they can, this mile-long track, and they'll try to get it almost up to light speed, then they smash them together and see what happens. And they smash them together, spits out different things. And they figure out, aha, smashed them together, and I got out some brand new element I just made, right? So they're just smashing the nucleus together, the nuclei together, seeing what happens. So let me just give you a few little uses. Yeah?
I was just wondering if it created a new element instead of being a compound because you cannot separate it, and it can't be reversed.
Well, I mean, compounds are always mixtures of 2 or more distinct elements, like water is hydrogen and oxygen. I guess I want to know. So you're saying this is not a compound?
Oh, no.
I see what you're saying. So you put 2 elements together. Why isn't that a compound that you make?
Yeah.
Is that what you're saying? Oh, I see. It is still one particle at the end with one nucleus. It's still just it's not like it still has two separate distinct particles. Yeah, I mean, they actually smush together and make something new. Yeah. But yeah, that's a good point. That's a good point. So probably the most common element used in nuclear medicine, or not in medicine, I mean, not nuclear medicine, but yeah, in general, medicine, the most common isotope you're going to see is this one called technetium-99M. And the M is just a little thing that means it's called metastable, which you don't need to worry about. But it just means it's not really one of the stable isotopes. It's kind of like a halfway point in between a couple of stable ones. But this is the one you most commonly see if you go on into nursing and health. Oh, by the way, I wanted to ask you guys last class, how many of you in this class plan to go on to 102? I'm just curious. Just only 2 of you? That's it? And the rest of you, what's your plan? You're going to go on to something else, or just doing this then as a total GE class? Or 108. Oh, we're going to do 108? Okay. Are you doing 108?
Yeah.
Oh, okay. That's okay.
Is that a big jump for 108?
Well, it's a little unusual. Normally you would do 100 or 108, and then you would go to 110, because 108 is the prep for 110. If you do 100, you would just go right to 110 as well, because it's basically a prep class too. But anyway. Okay. Okay, so you're going to do 108, a couple do 102. What the rest of you? Just 110, transfer, GE, what?
Microbiology.
Okay. Okay. So you're done with chemistry? You don't need any more? Or
I have to take some microchemistry too.
microchemistry? Okay.
So
Huh. Okay. What are you guys doing? Just curious. Anybody? Just general. Okay. Okay. Cool. Okay. Okay. So this isotope. So this is used a lot of times for various kind of diagnostic procedures. It's used a lot, like in brain tumors, liver exams, spleen exam, different things like that. But it's made by transmutation. It's actually made in a little reactor. So what they do is they take molybdenum 98 and bombard it with a neutron. So again, they smack them together, and they make molybdenum 99. And you don't have to memorize this whole sequence, but I'll briefly show you what happens. So you have a little mini reactor. You smash them together, make molybdenum 99, and that's not stable. So that spontaneously undergoes radioactivity, undergoes beta decay, and produces this stuff, technetium-99M. And then this decays by gamma rays, which is the thing they use in medicine, and is gamma rays to make real technetium-99, not the metastable one. That kind of stuff. So technetium-99M, basically, like I said, is just a little in-between state. It just has a little bit more energy than normal stable technetium-99. So remember we said gamma rays are the least ionizing, right? So they're the least damaging in that sense, but they're the most penetrating as well. Remember that? No? Yes. So let's say, when you use this, you're getting sorts of gamma rays. The gamma rays are nice because, again, they're highly penetrating. They would just pass right through your body, and they do very little damage on it because they're low ionizing. Versus, like we said, right, alphas hit you and they do lots of damage, right? And they actually smack you and they stop. Gammas just go right through you, pretty much most of the time. So, let me show you some different uses for gammas and stuff here as we go on here. Now, typically in nuclear medicine, you want to use things that have short half-lives, especially because those things that are being fed to a patient, right? You don't want them to hang around there for thousands of years in their body. You want them to have a short half-life and just be gone in a few days or a few weeks. So you're going to use short half-lives. And the interesting thing is, let's say you have radioactive oxygen versus regular oxygen. They react chemically the exact same way. There's no difference. So you give a patient radioactive oxygen, their body will use it just like regular oxygen. It knows no difference chemically. So you can do all kinds of cool things with that. So, for example, one I mentioned before was the isotope iodine-131. Iodine-131 is used like a thyroid diagnosis. So what you do with this is, let's say you have a thyroid problem and you want to make sure that your thyroid is functioning properly. Well, normally when you eat iodine, most of it goes to your thyroid, but you can't really see normal iodine. So what you do instead then is you feed them radioactive iodine. The radioactive iodine it goes through your body up into your thyroid, and then it spits out some little particles. Where is it out here? Beta particles, for example, right? So it spits out some beta particles, and then what you can do then on that patient, you put like a loaded around that patient, is you put like a little detector around their neck or whatever, and the radiation is going out of their neck. They can use like a little film plate or whatever, and they can see, okay, so is it functioning properly? You get like a nice little scan like this on a computer, and it shows, okay, so is the thyroid actually processing the iodine the way it's supposed to? And now they get little pictures by using, like I said, the radioactive version of the same thing. And then you can actually quote unquote see it in the body. You can actually see it working, which you couldn't do with non-radioactive, let's say iodine or whatever it was you're trying to detect. So there's a whole bunch of these that are used. I'm not going to go through all of these, but it's kind of interesting. There's a whole bunch, from gold all the way down to yttrium. But you do notice, like I said, though, they all tend to have short half-lives, right? So, a couple of days. Here's the longest one you'll see pretty much is this one and this one, 74 days. But most are like 6 hours, 13 hours, 68 minutes, right? So you don't want them to hang around your body for years and years spitting out radiation, right? You want them to be gone in a couple of days or a couple of weeks, right? And then stop working on you. So I mentioned this thing called Positron emission, and there's this kind of device called a PET scan. You might have heard of it in a hospital. It just stands for PET stands for Positron Emission Tomography. So again, what you do is you take an isotope that's normally used by your body, like oxygen, nitrogen, carbon, whatever. But you take a radioactive version that spits out positrons, like carbon-11, or oxygen is normally 16. How about oxygen 15? Nitrogen 13 instead of 14, things like that. And then you feed it to the person, and then again, what happens? Well, it goes to wherever you want it to go, their liver, their blood, their brain, whatever, and then you can do a little scan, and again then, the radiation passes, for example, out of your brain, let's say. So I'll just draw a little crappy picture up here on the board. So let's say you're laying down here. Here you are. Here's your nose. There you go. Awesome. So you're laying down here, and you feed yourself some positron emitting oxygen or whatever, and it goes up into your brain, right? Well, what happens? Well, the brain, with the fluorine reaction, whatever it is, breaks down and spits out positrons. And that's a penetrating, so what's it do? Well, it passes out of your body, right? Right, it penetrates out of your body. That makes sense? And then you just put a big old detector around this, and it goes off over here then into a little computer, right? Right here you are in a little computer, and you get nice little images that are showing you what's going on as the radiation is coming out of your brain, hitting the detector, and making it light up different parts of your brain, so you can detect it. Like I said, similar thing with your thyroid, right? So you have iodine, you put a little detector then around here, right? Right on your neck, and your thyroid spits out radiation. And then they can monitor what's going on with the radiation. Like I said, it's penetrating out of your body. So, you get all kinds of uses. So, yeah, so here's one of a PET scan. I thought it was interesting. This is a normal brain. And this is a brain here with Alzheimer's. So you can see there are certain functions or certain parts of the brain that aren't actually functioning as properly in the Alzheimer's versus the normal one and things like that. So, yeah, it's called a PET scan. Now, another one, like I mentioned, is gamma rays are really popular. Gamma rays are oftentimes used like try to kill cancers. You might have, I remember back in Sacramento, when I used to live there, I'd always hear these ads on the radio for a certain hospital and how what they called gamma knife surgery. So gamma knife surgery is basically kind of like this, where you're trying to use gamma rays as a way to try to kill off cancerous tumors in your body. So, what you do is, I will use this same crappy picture here. But now I'm going to change it up a little bit. So let's say, heaven forbid, you have a brain tumor. Heaven forbid. Okay. Well, what you want to do is you want to try to kill off that brain tumor using some radiation. So we're going to use gamma rays. And typically it comes from cobalt-60. Well, what you can do is you can put something like this. So you're laying down here, and this big thing just kind of rotates around your head like this. It kind of goes around a big circle, and it rotates. and it fires off gamma rays. So again, gamma rays we know are normally low ionizing, right? So they don't do much damage, right? But they're highly penetrating, which means they just pass right through your body. So what you could do is, let's say you have this little machine set up here, and you zap every step with gamma ray. Well, what happens? Well, it passes right through your body, hardly does any damage to you at all, right? Then we turn it a slight degree, and we do it again, 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 and 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 50 million times, whatever it is. Well, so what happens? Well, the tumor gets hit 50 million times, and it gets the business end of it. That makes sense? Because it's getting little, hardly damaging doses at all, but it will add up if it gets hit 50 million times. Versus in the healthy tissue, it only gets hit one time. Does that make sense? It goes right through, and then it's gone. Right through, and it's gone. Right through, and it's gone. Right through, and it's gone. But it's always hitting the tumor every time. Does that kind of make sense? Like your tumor gets hit 50 million times, the healthy tissues only get hit one time. So you see how that's kind of a smart way to do that, right? Because again, like I said, it's low ionizing, which means your healthy cells, they're fine. And it's penetrating, which means, like I said, it goes through, but it's gone, and it's gone, and it's gone, and it's gone. It's not hanging around for a long time. So that's how we can use gamma rays. And again, typically cobalt-60 is the source. So you got a big chunk of cobalt-60 up here. And it's putting out gamma rays. Like I said, we used to rotate it, right? So you see how... So obviously, you have to know, first off, where exactly is the tumor, right? So you're not zapping the wrong part. And you got to lay really still. And they put a little tattoo in your head if we're to shoot you at. And it's okay, hold still. And they zap you all the way around, right? And they hit you with gamma rays.
How effective is it?
Pretty effective. Yeah, pretty effective. Okay, so I want to spend a little time here on some fun stuff called nuclear fission. Nuclear fission. So nuclear fission is now where the atom doesn't just spit out like an alpha or beta, but it actually breaks apart. And the nucleus actually breaks apart into bigger chunks. So we're going to take a heavy nucleus and make lighter nuclei. So, for example, californium-252. You can make that stuff like in a particle accelerator, but it's horribly unstable, and it will just naturally fall apart. It just breaks off into a big chunk of barium and some molybdenum, and then 4 neutrons. So that's called fission. It just spontaneously just kind of crumbles. It's just way too big then. The amount of protons and neutrons is just not the good ratio, so it just falls apart. Well, that's spontaneous fission. But there are also nuclides that you can actually induce fission in. Now, the most famous of these, by far, is uranium-235, which is what's used in nuclear bombs, nuclear reactors, things like that. So, uranium-235 is normally just fine, just kind of, right? Just kind of fine, just kind of like chill out by itself, mind its own business. It won't do anything dangerous at all, unless you smack it with a neutron. So you got a little chunky uranium-235, you hit it with a neutron. It's kind of like you're playing pool in a sense. You're playing pool. Okay, so what you have then in the uranium then is a big cluster of protons and neutrons. This neutron over here then is your little white cue ball, and you hit it, hits the nucleus, and what happens? The balls just scatter, right? They go flying. So that's what happens here. So you hit it with one neutron, the nucleus just splits, makes barium, krypton, 3 other neutrons, and then an ass load of energy. All right. So now notice this though. What happens? One neutron starts the whole thing, but at the end it spits out 3 neutrons. So what happens? What happens then? Let's say then, if you have a big chunk of uranium-235, and you split that very first atom with 1 neutron, what's going to happen? So you split 1 atom of uranium with 1 neutron, and then it spits out 3 neutrons. What are those going to do? Split 3 more. And each of those is going to make 3, so now you're going to split 9 more, and then 27 more. And it just keeps snowballing. It's an interesting thing. So 1 neutron starts it, but once you get 1 to start it, you get 3 out, and they hit 3 more, and then they hit 9 more, and they hit 27 more, and they hit, 81 more, and this 243 more. It keeps on going and going and going, right? So, but that's with uranium-235. Now, most uranium, though, that you mine up out of the ground is not uranium-235. Most uranium is uranium-238. So if you just go out, out somewhere in the desert and you find a big chunk of uranium, it comes in an ore called pitch blende. Most of the uranium in that pitch blende, 99+% of it's actually uranium-238. Uranium-238. So uranium-238, if you hit that with a neutron, it just goes chink, think, right thunk. As it hits, it bounces off, nothing happens. It's only the uranium-235 that you can actually hit with one, split it apart, and release a bunch of energy. So that means, like I said, regular uranium you dig out of the ground, you can't use an atomic bomb or atomic reactor or anything like that. So what we have to do is we have to enrich the uranium. This is always the thing that's like always in the news, like with Iran and stuff, right? They're trying to enrich uranium, and they're trying to monitor, okay, so what percentage of uranium has been enriched. So what that means is exactly that, is they're trying to take the uranium-235 from less than 1% up to a higher amount like 10, 20, 50, 90, 95% uranium-235. So, how much do you actually need? Well, for like a modern nuclear reactor, you only need to enrich it up to about 3.5%. There's really no reason for you to have it more enriched than that unless you're trying to make a bomb. So, and for most modern bombs, it's up around like 90% or more. So you need to make it, almost entirely uranium-235. I'll explain why here in a second, okay? Now, the old school nuclear bombs back in the 40s we built, World War II, those were around like 60%, I think. So they were, crude by modern standards, but they got the job done, I guess, as you might say. So let me just go back here to this. So notice one neutron went in, right? Hit it, split it, spits out 3. Well, again, if those 3 can hit another uranium-235, that's going to split those 3, and they're going to make 9. If those 9 hit 9 more, then it's going to split it again. And you just keep getting the snowballing effect where every time you split one, you get a lot of energy. And then you get 3 times the energy, 9 times the energy, 27 times the energy. You just get a ton of energy coming out. So this is what's called the classic chain reaction, where all you need is one little neutron to start it, and then it's all just triples, and just keeps going. And like I said, so that's very self-sustaining at that point, because all you need is one to do it, and then once it does it, just makes 3 more, and keeps doing it. So let's think about this for a second. So this is why your uranium has to mostly be uranium-235. So let me just draw a little picture here. One of my last crappy pictures ever. I know it's sad, don't cry. So let's say I have uranium. I got a big chunk of uranium. I'm going to make, so all of these blue ones, and I'll make it in a big sphere, because you normally use it like in a sphere, like in a bomb. We'll just say that our goal here is to make a nuclear bomb, because we hate America or something, whatever we're trying to do here. I don't know. Okay, so let's say blue means it's uranium-238. So blue is uranium-238, right? Okay, well, so I come along and I fire a neutron at it. Tink, nothing happens. Bounces off, right? Right, because this version does not undergo nuclear fission. But let's say green is the uranium-235, okay? So this stuff is fissionable. But again, most uranium, only 1 in 100 are actually fissionable. So let's say that I happen to hit it just right, and I happen to get a neutron, sneak it in here, it smacks that right one. Kaboom, it splits! And then it makes 3 more. And they hit 3 neighbors, but what happens? Nothing. The reaction stops because the ones they hit just goes pink, just bounces off, nothing happens. Are you with me? So I have to enrich it. I have to make more of those uranium-235. Does that make sense? So now let's say these 3 were all uranium-235 because I had enriched it. Aha. Now we're in business, right? Because now then, that one hits that first one, and then those split and make 3 more, and this splits and makes 3 more, and this splits and makes 3 more. You see how that kind of works? But if these are all uranium-238, then the reaction just stops and it dies out, which is why you want to have lots and lots of uranium-235 in there. So that's good. That's the process of what's called enriching the uranium. So for a bomb, you want it to be, like I said, 90+%. So basically, there's almost no chance of you not being able then kind of keep the reaction going and continue it. Does that kind of make sense? So that's enriching, yeah.
So enriching is just upping the concentration.
Exactly. So trying to raise the percentage of uranium-235 from something less than 1% up to whatever you need. Yeah.
But it's not something that you do to 238 to make it 235.
No, exactly right. Yes, the way that it's actually is, okay, not normally done. There are actually several different ways of trying to enrich uranium. The way they used to do it then, like way back when, was one of 2 ways. One was to actually grind up all the uranium, and the uranium-238 is a little heavier, obviously, than uranium-235 because it has 3 more neutrons, but it's only slightly heavier. And they would actually try to separate them out by mass, and it just took forever. Try to pick out the little ones that are just a little itty bitty, teeny tiny fraction heavier, and pull those out, and then keep on pulling them out, and thing. And another way they did it was with gases. They would actually take the uranium, reacted I think with, I remember it's fluorine. It actually turns it into a gas. And the same thing. So they tried to separate out the heavier gas that had the uranium-238 from the lighter weight gas that had the uranium-235. And they would go back and turn it back into uranium, and then they separated it out. Again, that was a huge part then of the whole first bombs we had to make, was trying to figure out how do we enrich this crap. I mean, how do you do that when they're only super slightly different? I mean, again, they're both uranium, so they both chemically react the exact same. You can't separate them out chemically at all. You have to figure out some other way to do it. So anyway, yeah. Like I said, so it hits 1, makes 3, those hit 3 more, make 9, and then it keeps going, just escalates. Now, the minimum amount you need of the uranium-235 to actually create a self-sustaining chain reaction where it just keeps going enough, that's called the critical mass. So that's called the critical mass. So that's the minimum amount you need to actually keep it going. Now, for example, let's say your goal is to make a bomb. Hopefully it's not. And if it is, please don't kill me. You don't learn from me. You need a certain critical mass, right? So, let's say you don't have enough. Let's say you just have a little itty-bitty tiny chunk of your enriched uranium. So you hit it with 1 neutron, and it splits, and it splits, and it splits a few more, but then they all quickly leave the uranium, and the reaction is over, and you never get enough bang out of it. So what you need is one of 2 things to happen. Either you need to get a much bigger chunk so it can actually split, and then split, and then split, and then split, and then split, and you do get enough for a nice sustained reaction. So you need a bigger chunk. And typically then for the bigger chunk, you need it to be about 52 kilograms, which is about a 17 centimeter sphere of uranium-235. Pretty good sized chunk, right? 17 centimeters. Okay? The other option is I need to get these neutrons to somehow turn around and go back in and keep smacking the uranium again and again that hasn't yet reacted. What you can do instead, the other option, is you can surround it with a neutron reflector. So, a very common one is beryllium, the element beryllium. So you take this, and now it splits a couple times, and they try to escape, but nope, they hit the mirror basically, and they reflect back in and hit some more. Try to escape and reflect and hit some more, and that kind of keeps the reaction building, until you get the big kaboom you want. So 2 options, either have more of it to reach critical mass, or surround it with a neutron reflector and redirect those neutrons back in, and keep hitting it again, and keep hitting it again, and keep hitting it again. So that's the 2 options. Okay, well, this is all relatively new science, you got to realize, right? This is all, basically started back in the 40s, so it's not that old, 70 years old. But back in the late 30s, early 40s, U.S. scientists realized that the potential for this, right, to actually cause a chain reaction, and a self-amplifying bomb, basically. We're just kept on amplifying and getting bigger and tripling and tripling and tripling. It could just grow just exponentially. So they were concerned. They were concerned about this. So what they did was they reached out to this guy you may have heard of. His name was Albert Einstein, and they asked him to write a letter then to this. And they asked him to write a letter then to the president, Franklin Delano Roosevelt, FDR, to kind of warn him then of the whole possibilities of this new type of a bomb being built, and how the Germans they knew, well, not knew, but the Germans they kind of suspected were also working on this atomic bomb. Well, so Einstein, of course, was himself, originally German. He'd already left Germany and come to America, so he said, okay, so write this letter. So Einstein wrote a letter then over to FDR. Here's a little picture of the letter he wrote from Einstein to FDR, and he wrote in part of it, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type, carried by boat and exploded in a port, might very well destroy the whole port together with some of the surrounding territory, which of course we now know is a vast understatement, right? So Einstein's thinking, well, maybe you have it on a boat and it blows up up to like part of the harbor or something. But now we know it blows up the entire freaking city right now. But anyway, so FDR wrote this. And so FDR then actually read this and he said, okay, Einstein, sounds good. You're a smart guy. I'm going to trust you. And he decided then to form this thing called the Manhattan Project in 1941. And the goal of the Manhattan Project was basically to win the first nuclear arms race and to try to build an A-bomb before the Germans built their A-bomb. So they went through this whole thing, and they scoured the country, and they found the best and brightest physicists and chemists, and the man in charge, this guy named J.R. Oppenheimer. And he was put in charge of the Manhattan Project. And again, they had all kinds of logistical things to figure out. So first they had to get the uranium. Then they had to figure out, how do I actually enrich the uranium, right? Like I just showed you, right? I said it, which is an extremely tedious process. And then once I enrich it, well, I have to actually get enough of it, to actually make the bomb. It's called the critical mass. And then once I get the mass, how do I start the reaction? Where does the neutron come from? And once I figure out that piece, how do I actually take the thing and actually deliver it in some kind of a conventional bomb shape that still has the critical mass with the neutron creator and all this stuff. So, it was a whole logistical thing. And they had sites set up all over the country, each working on them basically like various little small pieces of the puzzle. And only actually a handful of men actually knew the whole piece of the puzzle. So so he actually knew the whole piece of the puzzle, FDR. But in reality, though, most of the sites all over the country had no idea what they were doing. So for example, one site might be told, okay, so your mission is to figure out, how do I enrich uranium? Why? Don't ask questions! Just figure out how to enrich the uranium. And your mission over here then is to figure out, how do I deliver a single neutron in a portable manner? Why? Don't ask questions. You just figure that out. And then, like I said, and once they were all kind of done separately, it was all kind of put together, right? And they kind of, did it. And it is kind of amazing too. How many thousands of people worked on this and had no idea they were doing it. So yes, I saw a photo actually recently, and it was a big factory, maybe in like Nevada or something like that. And it's a giant factory, and they had like thousands of workers there. And the workers there then in that factory, they were actually trying to separate out the uranium-235 from the 238 in the factory, and it was the whole enrichment thing. But the factory workers didn't know, what they were doing at all. Actually at all in the factory. It was basically then they just come to work every day, and they would go there, in the factory, and they would pull their levers and turn their knobs and watch their dials without any idea of what they were actually doing when they were pulling those levers and turning those knobs and things like that. Like I said, so it was kind of crazy. It was super secretive and hush-hush and very compartmentalized.
Looks young.
Well, like I said, this is 1941, so what do you be? 37. You're 37, so. Yeah, so anyway, so it took us about 4 years, the Americans about 4 years, but they did do it, and they did make their first atomic bomb, and where better to set it off than in your own backyard there in New Mexico. So they blew right up there in New Mexico and said, okay, so So you'll see how it does. And it blew up to a force equivalent to about 18,000 tons, not pounds, tons of dynamite. So keep in mind, a ton is 2,000 pounds. That's 36 million pounds of dynamite. 36 million pounds of dynamite. That is a crazy big explosion. And here's a lovely picture of it there, blowing up in New Mexico. So that was the right there. It blew up right from the backyard. 36 million pounds of dynamite.
Is there still a lot of radiation over there?
I don't know. I would assume it's probably all still blocked off. And yes, I'm sure it's all still. Yeah. So yeah, like I said, but it was finally done. The interesting thing was, if you know anything about history, was by July of 45, the Germans are already surrendered. By this point, the Germans are already surrendered, but the Japanese were still fighting. So they took the bomb instead over to Japan, and they actually, after 4 years of all this enrichment and trying to, of enriching and collecting it and doing anything, they actually still only had enough enriched uranium-235 to actually make 2 bombs, one small one and one big one. Of course, the bombs you probably know, the bombs names were what? What the bombs names were? Fat Man and Little Boy are the 2 bombs. Fat Man was the bigger one. Little Boy was the smaller one. And they went over to Japan and they bombed it twice. And they said, "Okay, Japan, there's more where that came from. You guys don't." They were like, "Okay, we surrender." But again, because there was no more, right? Wherever you spent 4 years just getting that little mound. That little mound. That comes the big secret, right? We told them, okay, there's more where that came from. You guys better surrender, but there wasn't any more, right? We kind of spent our entire load on those 2 bombs, and that was really all we had. But anyway, but it works. It's okay, fine, we're done. We surrender. So that was the not so happy use of nuclear power. Now, the more pleasant use of nuclear power is in nuclear reactors. And again, like I said, a nuclear reactor, now we don't need 90% enriched. We need, 3.5% is plenty of enrichment for our goals in this. But it basically works just the same way as a coal-powered plant or a natural gas-powered plant, where you're just trying to generate heat in order to boil water. The water turns into steam, and the steam then escapes and it powers a big turbine and generates electricity. But in a nuclear plant, though, then, but the nuclear plant, though, then, the way the water is being heated up is not through coal or through natural gas, but it's through the energy that's coming off of the uranium being split apart and undergoing nuclear fission. Okay? But same kind of deal. So let me show you a couple of pictures here. Now you notice in every reactor, I've heard this before, like in movies and things, they have these things called the control rods and these things called the fuel rods. Maybe that term sounds familiar from movies or whatever. So we have the fuel rods, and the fuel rods are the stuff that are made up of the uranium, right? So this is my uranium. So these are made up of, the enriched uranium-235. But again, it's only about 3.5%. Okay? And then in between those, we have these things called control rods we can raise or lower down in between the fuel rods. So let me draw another little crappy picture. So let's say these are my uranium fuel rods down here, okay? These are my uranium fuel rods. And again, they're only 3.5% uranium-235. So the reaction has been started, we'll assume, and it's spitting out a neutron, right? So it spits out a neutron, let's say on this side. Well, actually it spits out 3 neutrons, right? And it may or may not hit another uranium-235. Right? That makes sense. It's a 3.5% chance it will hit another one. And if it does, well, that one spits out 3 more. But if not, then the reaction kind of stops, made a little energy. But then another one, is hitting, spitting out 3. Another one spitting out 3. And again, another one spitting out 3. Oh, whoops, there it goes, hits one. So that one happens to spit out 3 more back then, right? So it's kind of, so again, it's much slower and kind of controlled. Well, then let's say, the reaction's really, it's really going, it's really picking up speed, and it's really starting to hit more uraniums, and you want to slow it down. What do? Well, then that's where you have these control rods. So you drop inside in the middle of these another rod, which is made up of a neutron of a neutron absorber material. So now the neutron goes out, smacks that rod, it's actually absorbed, and it just stops the reaction. So you can totally kind of slow it down with these control rods sliding down inside. So typically, what they use for that, I didn't mention it here. I thought I had it on here. They typically use, well, there's various things you can use. The most common, I don't know if it's the most common, one of the common ones is an element called hafnium, HF, which is an odd little element. And I had a student one time, she'd been in the Navy formerly. She was stationed on a nuclear-powered aircraft carrier. Her name was Jackie, and her job actually on the aircraft carrier was every hour on the hour, she had to walk inside the nuclear reactor, and she had to actually visually inspect the reactor. So she had to get outside the reactor, get outside the reactor first, put on like her big old, white radiation suit, walk inside the reactor, walk around it, visually inspect it, come back outside, hose off. I do that every hour for I don't know how many years she's on that stupid boat. It was like the worst job ever. Your job is to walk inside the reactor once an hour and visually check it out. But anyway, but those reactors, for example, these control rods, supposedly, we're going to have hafnium, like I said, which is another element you'll find on your table, right? So again, hafnium, like I said, is a neutron absorber. So neutrons are spit out, but it hits that, and that's it. So it absorbs it, and the reaction kind of stops, and the reactor, like I said. So if you lower them down, less energy. You pull them up, it's full speed ahead. You're getting lots of energy. You really power the turbine, crank with the electricity. Okay. So that's fission, where you're splitting nuclei apart into smaller ones. Well, the opposite of that is what happens in the sun, which is nuclear fusion. Now you're taking smaller ones and you're actually combining them together into bigger ones, or you're fusing them together, which is why it's called fusion. So now this is much harder to actually start a fusion reactor. Or a fusion reaction is much harder than to actually start, because it takes so much energy to actually force them together and actually make them stick and combine together in a sense. But if you can get it going, then in the end it actually releases even more energy than like an actual fission reaction, like a nuclear power plant or a bomb. So I mean, way more energy comes out. But the nice thing about it is, though, is you'll see it's much cleaner than a nuclear power plant. Because in a nuclear power plant, now you have all this extra waste to get rid of, right? Right. Once the uranium then has reacted, now it's turned into thorium and plutonium and different things like that, and that has half-lives of millions of years. You have to go off somewhere, then like in Utah, and then bury it somewhere on the ground for millions of years or whatever. That's it. Right, so all this waste you got to get rid of. But fusion doesn't do that. Fusion, we'll see, is nice. So again, the sun basically is a giant fusion reactor operating at millions of degrees Celsius. So let me show you what goes on in the sun in terms of nuclear fusion. So now, again, fission was taking a big one, splitting it into smaller ones. Fusion is taking small ones, combining them into bigger ones. So there's a few basic reactions. Now, the sun is mostly hydrogen. It's about a fourth helium, then 1% little random elements, but mostly hydrogen with about a fourth helium. So what happens? Well, it's a fusion. So imagine two hydrogen ones. Right, it's super hot, so they basically fuse together and become a hydrogen 2. And then a hydrogen 2 and a hydrogen 1, they fuse together and make a helium 3. And then a helium combines with a hydrogen 1, and they make a regular helium. You know, regular helium gas, right? Right, you know helium gas makes your voice squeaky. Stuff here. Helium 4. But again, but every time you undergo fusion, it also releases lots of energy. But the nice thing is though, is your waste in the end is what? What's your waste in the end when you're all done with the reaction? Helium gas. Who cares, right? You blow up some balloons with it. Big deal, right? So I mean, it's great. There's no kind of radioactive waste, like I said, at all. Right when you're done, all you make is some helium gas, and you get lots of clean energy and no radioactive waste. So it's a much better process. But again, it's so hard to start. It's so hard to start because it takes millions of degrees to actually get this going. We can't. The volcanoes are hot, but they're thousands of degrees. We need millions of degrees of energy. So it's just really super hard to actually start a fusion reactor. So one thing, I have another slide here. So one thing that can happen is, I have a slide I'm going to show you just real quickly from my other class, my 111 class, because I think it's a fun slide. So what needs to happen then? Okay, you hate me. Let's say we have a fusion reactor, and you're going to get up to millions of degrees. Well, the problem is, how do you contain a reaction at millions of degrees? I mean, what kind of structure can you build it out of? I mean, steel? No. I mean, steel will just melt, right? Concrete will just melt. I mean, what do you contain a reaction that's going at millions of degrees? So the thing they have actually then tried to postulate are basically they're very sci-fi. You're trying to basically use them like a force field. So you don't even have a physical wall. So the wall around it is just a wall of pure energy. And the most common one is using like magnetic energy. So you would just use like a giant magnetic field. Son of a gun. And you would just contain this millions of degree reaction in a big magnetic field, like let's say this. And then inside it you have your own little fission reactor here, right? So here's the sun inside it, but you're trying to contain it in a magnetic field. And again, this wall is pure energy, so these walls can't melt, right, when you're trying to contain it. But again, it's super sci-fi, and it actually was in a movie a few years ago, which is why I want to show you this picture. You recognize it, huh? What was it in?
Nothing.
Tell me, you know what it was in? It was in Spider-Man. It was. I have a picture here.
Is it the...
And Doc Ock.
Yeah.
Yeah, Dr. Octopus, I mean, yeah, that's what he was doing. He's trying to build a nuclear reactor. Not a nuclear reactor. A nuclear reactor, but it was a fission. Not a fission, it was a fusion reactor. It was actually exactly the way it might look, like I said, where there are no actual physical walls containing it. It's kind of hovering in space with like a magnetic field just kind of containing it, right? So it is a fusion reactor. And then there was a story that was really big news. It was last semester, must have been like October or November, where I think Lockheed Martin supposedly has said they're going to have a fusion reactor, a portable fusion reactor, built. You have to be hauled around on a small truck, built actually viable in the next 10 years, they said. And if you could actually build a truck portable size fusion reactor, that would be, that would solve all of our energy problems overnight, because now you would have a source of energy, like I said, a source of energy, and just burns hydrogen, and all it makes out is just helium gas, right? There's no way. You can just produce hydrogen all day long out of just water in the oceans. We could just make endless amounts of energy, super clean, super waste. But the risk is, you are hauling around this thing that, like I said, it's burning at millions of degrees, and you can't contain it into a wall. And if it doesn't escape, what happens then? Well, then it melts through your walls, your building, and your planet, or whatever happens. Who knows? But anyway, so we'll see what happens.
Wait, is the force field containing the heat, or just everything? Like, that's a...
I'm just containing. It contains the particles for sure. Now, I'm not sure all the heat's being contained, but I'm not sure about that. But again, like I said, it's all kind of crazy science fiction. But like I said, but it actually is coming to pass, like I said. So hopefully, we'll see. But like I said, but in theory, they're saying in the next 10 years, we'll have a portable, truck-sized fusion reactor. You can just haul them all over the place and just park them in all kinds of remote places and power entire cities with one little pickup truck. It'd be crazy. So that is it. That is my last slide forever for CHEM 100. So let me pass back part of your exams here.